Okay, yeah, welcome to this week's SBCL Bcast. It's my great pleasure to introduce a good old friend and colleague, Stefano from the KTH Royal Institute of Technology, who's going to tell us today, who fortunately agreed to tell us today about his experience with physics-informed neural networks, where he just recently wrote a wonderful kind of survey style or experience style paper that I really enjoyed reading. So I'll give the word to Nikolai to introduce him a little bit more.
Okay, and thank you, Torsten. And again, thank you, Stefano, for agreeing to come in and give us a talk. So Stefano first studied in Torino, Italy, and then got his PhD in nuclear engineering from the University of Illinois at Urbana-Champaign, the United States. And he is now an associate professor at KTH in Sweden, where he does work on both exascale computing, numerical solvers, differential equations, and now, of course, deep learning for numerical methods. He has won R&D 100 award, multiple best paper awards, and without further ado, I'll let him go ahead and tell us more about these physics-informed neural networks.
Thank you very much, Torsten. Thank you very much, Nikolai, for this big opportunity. It's an honor for me to be with you today and be able to talk at SPCL broadcast talk. Today, I want to talk about a quite intriguing topic that is to look at how to combine traditional scientific computing approaches with the emerging technique, mostly coming from neural network machine learning, into something that is new, some new numerical methods. What is the path to go there? I have divided my talk in three basic parts. I've spent quite a few time on going on description of PINNs or physics-informed neural network. I want to give you just one example, more a motivating example, just good for introducing the topic, but some useless example, and then I will talk about PINN and how he solves some of the issue from this very naive neural network. I will then spend some time on looking at a few things that we can do in tuning the performance of this physics-informed neural network. And then I will finalize my talk talking about probably the most exciting part of future work, that is how we can integrate physics-informed neural network machine learning technique into traditional solver to go beyond on what we have today. So the main topic of this talk is PINNs, that stands for physics-informed neural network. I have to warn you that PINNs have many usage, including data assimilation. So we have data, we have models, and when we want to assimilate the data in our models, uncertainty quantification. So for instance, a parameter is unknown, or we have certain uncertainty, we can do this kind of stuff. Also, it's quite powerful in solving so-called ill-defined problems. So we do have a governing equation, but we miss boundary condition, or we miss an equation to close the system, the so-called equation of state, and the PINN has been used to tackle this problem. Today, I want to focus on PINNs, or physics-informed neural networks, solely for solving partial differential equation. So given a classical problem of scientific computing, that is given a PDE, how we are going to solve this PDE. So the PDE will have a structure, will have boundary condition, might have initial condition if there is a time involved. So just want to emphasize this point. I'm focused on a small part of our PINNs that is dedicated to solve the PDE. However, I do recognize that there is a big part of literature, studies of physics-informed neural network that is dedicated to the data to different tasks. The particular topic that I want to talk about is I will focus on an equation, the 2D Poisson equation. This is just an example that is quite common and quite is omnipresent in scientific computing. Maybe electrostatic equation for electrostatic system, or maybe a pressure solver. It comes up quite often in many different applications. When I talk about a linear solver for using neural network, I'm talking about training a network in order to learn how to solve it, and the prediction step, where we take the neural network, we provide a set of numbers, and then the network provides us the solution at the points that we decide. So we focus on all these presentation focus on solving this two-dimensional Poisson equation, and then we are going to treat this neural network as a solver. Having said that, this PINN neural network can solve any PDEs, including nonlinear terms. So this is quite a simple case that I want to just showcase today for illustration purposes. However, PINNs they apply to all range of different PDEs. So the first question I would ask you, this is the equation that I want to solve. I know the basics of machine learning, how forward pass, backward pass working, loss function. So the first question I have for you is how you do it. How given this equation, how you probably tackle the problem. Well, to simplify, let's say that we do have the analytical or the numerical solution of this Poisson equation. Well, the way probably we'll do in case of having analytical solution, I just take a neural network that we fix the number of units, the number of layers, and then we provide full connectivity. And then what we do is we choose a point on in the domain. We put as the input of our neural network. We make it through this neural network through a forward pass, and then we calculate what is the value of u, that is approximation of the solution of our problem. The next step is the next step. We know this point what is the analytical solution. So we have our approximated solution that is u tilde, and then we have the analytical solution that we know a priori, because we want to train with some knowledge about the solution. And then we calculate an error. In this case, we take the square of the error. We want to do this for several points, the so-called training set. So in this particular case, our training set will be a different point within the domain. For each point, we have a forward pass. We calculated the error when we calculated the loss function. It's kind of average of the sum of this squared error. This error then is used to propagate back and change the weights and the biases of these units. So this, of course, works very well in the case of having analytical solution, because we can choose this as kind of supervised approach. We know we can easily calculate the error knowing the analytical solution. We can do the very same things in the case that we have, instead of having analytical solution, if we have the numerical solution. In this case, we are not as much as free as choose where to pick it up our points that are going to give as input to the neural network, but our solution will be known at a certain grid points on the domain. So we know the solution only on this point. So the procedure here, in the case we know the numerical solution will be very similar. We have all our point, we gives the x and the y as an input. We can calculate the error from the knowledge of the numerical solution on the grid points, and when we use this error coming from the loss function to propagate back and adapt and change the weights and the biases of the neural network. Once our neural network is trained, the biases and the weights of these units are fixed, and we can just use as our, to predict the approximated values of our solution U tilde at a different point. Note that PDE solver defined in such a way is gridless, so it doesn't really require us to introduce a grid into the system. And this is also true in the case we just train just on a certain point. So it's one interesting part of having this kind of solver, also the fact that we can pick it up any point in our system, and then we will get the approximation of our solution at a given point. Of course, at this point, probably we all realize that yes, this approach gives some insights. It will be probably the zero order solution that we find to the problem that I told you, solving a PDE. Of course, it's not very useful to be optimistic, since we already have the solution. So there's not really a big step ahead. So the PINN is really addressing some of some of this issue that I just presented. So the PINNs are neural networks that encode the partial differential equation into a part of a neural network. So we will have an extra part added to our first network, and this network is used quite exclusively to calculate the error, the so-called loss function. We will still have the first part of a part of the network that we saw before, that is used to give these approximated values for our function. So that part we will call surrogate, right? Because it's tried to mimic very closely the solver. What are the major innovation of the PINNs when it comes to the solution, the naive solution I presented in the previous slides? Well, probably the most important innovation is really to add a new part to the network itself that is dedicated to calculate the residual. The residual is basically a proxy of the error, how far we are from the solution. And this part of the network that we use to calculate the residual or the error is the part where we are going to encode the partial differential equation into the neural network. So that's a major innovation. Also, we are going to leverage one of key features of a neural network that makes so powerful, the fact that they rely on automatic differentiation to calculate derivative and differential operators on a graph. So here I mentioned here the paper by Raisi, Perdirakis, and Kardiadak that pretty much open up. Was probably one of the first, if not the first, to introduce PINNs in the community. So as I told you, let's look at the first innovation of a PINN. We have the part of the network that we had before. We have our input X and Y, and then we have the part of the network that is dedicated to split it up, given the X and Y, to give the solution U tilde at the position X and the Y. In the previous slides, we had the analytical solution to adapt the weights and the biases of this neural network. In the case of the PINN, we add this additional part to the network. So this is called, what is often called a residual network. It's not a ResNet, it's something different. So there's sometimes a lot of confusion, right? But if you're coming from linear solvers, from numerical analysis, you probably recognize, you probably will think residual as a so-called residual function. That is just basically how far you are from solving exactly these equations. In the particular case of solving the 2D Poisson equation, the residual function is basically just the Laplacian, and then minus f, that is the source, the driver of our PDE. So what we're going to do, we're going to take this residual function and try to encode it on the network. So we will add additional units. Part of the network will be dedicated to encode this residual function. So there's a part here to calculate first order derivative, and then the first order of a first order derivative. So that will be second order derivative. And the top part will be for the x direction, and the bottom part here will be for the y direction. And after we calculate this, the residual part for the Laplacian components, will basically subtract our source term. In the residual function network, we will also include the boundary condition. So we can it here. We require that on the boundary, we know what is going to be the solution because we know the boundary condition, and we are going to put these constraints. So the nice and innovative part of PINN is actually to add this additional part to the network that we had before, in order to calculate the error. Right. So the residual function, it is a proxy of error. Once we know what is the residual, so what is the how far we are from satisfying the function, sorry, the residual function, we can calculate this loss function that will drive the optimization of the weights and the biases in our surrogate network. So that's the most and probably the leap the major leap that we do when dealing with this physics informed neural network. So a major difference with the naive and a kind of useless approach that I presented in the first few slides is really that the fact that we add this residual function network allow us to not to know what is the solution, right? So we don't really need the values in order to do this kind of supervised learning. What we are going to do here, we just give the input, we calculate what is the approximate solution at the point X and Y, and then we feed into the residual function network to get one residual. And this residual will give us an error, and that this error we're going to use to feed back in the weights of the surrogate network and change and optimize the values of the weights and the bias. So in some sense, this can The PINN, it might be a structural language here, but it allows some supervised training in the sense that we don't need anymore to know either the analytical solution or the discrete solution coming from using some numerical technique. Some of you who probably work on linear solver before saw this. The very same technique is at the base on iterative solvers. If you have used Krylov solver, the basic technique is really is to find iterative algorithms and find in each iteration the vector x that minimize the residual. And you see here is basically this almost the same definition that we had for the error for our PINN. Right? So these two here at the bottom is the Euclidean norm, and this is our residual. Of course, the Krylov solvers are much more advanced technologically. They know how the space, they use properties of the Krylov space and go directly to the solution. But the technique that adding this residual, for many of you probably reminded of user of residual and optimizing the direction to go to the minimum of the residual. This is the first major innovation. So adding to a surrogate network that give us approximate solution of our partial differential equation. This extra part of the graph that is the residual network. The second innovation is really to leverage one of the important features of machine learning algorithm that rely on automatic differentiation as opposite to typical numerical methods that rely on numerical techniques, so numerical differentiation. So for instance, you probably have been used during your studies, your career, finite difference methods, or no, that's numerical differentiation. Here we are talking about automatic differentiation. So this automatic differentiation is quite beautiful and elegant in many senses. Is very similar to symbolic differentiation, so exact differentiation on the graph, and is basically just applying the chain rule, the calculus 1 theorem on how to calculate derivative of a function here come up from the past of our study, and is very powerful, also very beautiful technique that machine learning like backpropagation and forward propagation use quite strongly. Important part is also that this kind of technique is available in TensorFlow, PyTorch, all the main frameworks. Is a key feature of deep learning frameworks. So here I just present very nice in survey, and also very nice comparison between automatic differentiation, numerical differentiation, and symbolic differentiation. And also here I show how convenient in to use the automatic differentiation in deep learning frameworks. So my guess also we will see more and more of this automatic differentiation on scientific code. So also is quite exciting technology. So a second important feature of PINNs is really to have this automatic differentiation in order to calculate this differential operation on a graph. And this comes basically for free from using the network graph formalism and the deep learning frameworks. So then once we have the train, so our solver is basically trained the network. So instead of if we have iteration of our training, this somehow equivalent to our solver iteration. We'll take a training iteration to converge to some approximated solution. And once we are happy, we can just take this part of the network, the surrogate, and then we take some points where we want to know the solution, and we just make a pass of our network and get the solution. As I told you, one of the beautiful part of PINNs are really the griдлess, so you don't really have to take a grid. Of course, if you're interested to know what is the values of your approximated solution at a certain point on the grid, you can introduce a grid and then just give as an input point the nodes of our grid. A very interesting part is really how to formalize and provide a strong theoretical background to PINN. PINN can be seen in as an iterative solver, and also can be very similar technique that being used in classical numerical analysis, can be used for convergence stability studies. So that's particularly important for the future of the methods. The fact that the community has been putting the foundation for a quite solid understanding of how the error propagate, how the error diminish, or in case of stable goes up. So it's possible there's been quite a lot of work on defining different errors that they have similarity with classical numerical analysis, but also they go beyond from the fact that we are talking nowadays about training, validation, and generalization. But the exciting part is really the fundamental formal work that has been put in place, and I want to mention these very beautiful papers that if you want to know more about PINN and have a strong formal background on understanding the basics of PINN and what was the first principle, strongly suggested is a beautiful paper by Michel and Molinaro at ETH. Beautiful work. And also this work by the group by Karniadakis at PNL on defining errors. So one of the practical aspects is being shown by some papers, particularly by Michel and Molinaro, that the roles of activation function on also necessity to have sufficiently smooth activation function. So activation function, for instance, they don't have discontinuity on the derivatives. So, for instance, activation function that are not sufficiently smooth, like rectified linear ReLU and LU or CeLU, they do not converge. So this has been shown. But also, if you, like myself, I play a little bit with the different activation function. You want converge to, you want to decrease the error, increasing the number of iteration. So the major point I want to make on this slide is very exciting, the fact that there's quite a bigger effort on formalizing that framework, the mathematical framework, and to do some very nice enlightening analysis. So, particularly these papers, but also papers from the very same author along the same line. So as a person interested in understanding how the PINN work. And one major question was very practical. What is actually the performance of a simple PINN when compared to a traditional solver? So I just took as an example, the Poisson to the Poisson equation. I put this driver for our PDE. I will explain why later on, why I choose this particular one. But you can say that these have a different signal, a different wave number, right, from big scale to lower scale. So I wanted to have a different signal at a different scale, but I will explain a little bit more later. When I took a rather fast in this approach, I used this Python and this deep XDE domain-specific language for developing PINN. And very quickly, I was able to solve this very simple problem. I used four fully connected layers, 50 units, tan(h) as activation function. And then as a training, I took 10,000 collocation points. So the input point I chose randomly within the domain. And then I ran the simulation without knowing anything. I pretty much follow what are the settings by default. So I didn't try to optimize. And that's what I got. So here we have on the x-axis on the plot, we have the number of epochs. That is one epoch is necessary for going through all the train data sets. So I go through 10,000 input x and y points, and we will have I think 25,000 or so epochs. So this is the number of epochs, and then you see how the error goes down. It goes around quite quickly, very beginning, and then here I switch the optimizer. So I go from Adam to a second order optimizer called the BFGS, and you see that then also it decreases in a different way. So this is the training set. I just used the default values that I found in the literature or in the framework itself. So these points show what is the solution at a different time. So here we have 500 epochs, so that is this point here, and then we have 5,000 that is here, and then here we have at the end. As you can see here, we have, yes, a very fast convergence here, but solution doesn't look very good. So the error is quite big. Going forward, then you see that the error at the end after roughly 23,000 epochs is it looks okay, right? But if you look at the error here, that is I know what is the analytical solution from this very simple source term. I can calculate the error, and you see that most of the error is around this 10 to the minus 3. A lot of is around this the boundary. So probably the most shocking for me and time, I would say, disappointed part of PINN was really the time to get to this solution. It was almost like 2 hours. It was on my laptop, not the best one, but still I could solve using PES-CCG to bring this to fully convergence to machine error. It took me 92 seconds on 128 grid. So we're talking about order of minutes to order of hours to get okay solution. So then I was saying, you know, let's see if there's any possibility to actually improve, or you know, is really desperate case, or is something that we can do more. And this brings me to the second part of my presentation, that look at, you know, how tuning a PINN solver. And I will go through some few, for the sake of time, some few things that I experimented in this work. Well, so that we can expect, you know, activation function. I already mentioned, you know, the fact that non-sufficiently smooth activation function gives a problem in the convergence, and decreasing the error, increasing the number of iteration. Also, just making very quick similarity between activation function and you know, trial and wait function in FEM methods, in finite element methods. There are different works that show similarities. Of course, trial wait functions are linear. In the activation function, we bring this nonlinear part. But basically, our goal with the neural network is to approximate the solution with a certain function. In this case, activation function that takes you know, a specific argument. So intuitively, we want to have a good interpolation function that is capable of describing our solution. So as you can imagine, there are, depending on the problem, in this case, depending on the source term, on the how smooth it is, the source term, different activation function can be you know, more or less better. So I took, for instance, experiments just quite a smooth different frequency, and then one that is just discontinuous. So it's one within like a circle, and then the rest is 0. And then I try you know, different activation function, and of course I found that you know, quite a smooth activation function like tanh or you know Swiss are quite good. They have a small error for this smooth driver. On the other hand, other activation function that are steeper, like in this case, like a sigmoid, are better in the case of representing, taking care of discontinuity in the source term. So activation function matters quite a lot, and also they are problem dependent. In this case, source dependent. So it's some tuning that can be done there to easily get some gain. Another important factor in PINNs, you see that you also will get quite easy gain by using adaptive scaling, adaptive local scaling, so-called LAF activation function, that basically have adaptive scaling to each layer of the network. Even you know, more adaptive scheme can be used. In particular, this is quite powerful. Well, it's quite effective in dealing with the issues at the boundary condition that we saw in the previous slides. This is a common problem in the neural network, this vanishing gradient problem. Another key technology is really the optimizer. As I mentioned, we use second order of the optimizer, and it's a critical technologies for PINN. One downside of the PINN, probably at this point you already realize, is the fact that if we change the source term of our PDE, we have to retrain, right? So we do again other iteration without getting you know, any more information from what I've done before. A typical case in large-scale simulation is actually to solve the same equation with the different sources. So we go one step, we solve this equation, and then the next step we have a slightly different source term, and we need to solve the same problem. So we can also use quite well, you know, transfer learning. I show here in certain cases, you can have quite a big speed up. So transfer learning, the fact that we can initialize the weights and the biases of our neural network using the results we already have from the previous training of neural network solving the similar problem works quite well. There's a little bit less work on understanding the impact of different architectures. Most of the PINN today are fully connected. Of course, this kind of ideal case for elliptic PDEs, because in elliptic PDEs, the information propagates instantaneously, so the velocity is infinite. So that's also mean that we needed kind of connectivity. There are some ongoing research on architecture that dealing with with the time, right? For instance, hyperbolic, parabolic, like a wave equation, they need to do that. But so this is some exciting work to map networks to the nature of the PDE. Finally, I want to spend a little bit time. Time is running out, unfortunately, but on the last part of my presentation and how to integrate PINNs into traditional solve and what is what are the principles that should drive our integration. Probably for me, the most enlightening idea and principle was to learn about this F principle or frequency principle that is explained and in these two important papers on these two first paper, and also again proven in PINNs by the Karnagatis group. But what is this? Well, basically, this principle, the experimental observation, is that deep neural network often fit targets function from low to high frequency during the training process. So what does this mean? Well, it means that if we have a solution, for instance, we have this is our solution, we can decompose our solution in different sinusoidal sum, so like a zero, constant, and then low frequency, like a big, large scale, to high frequency or high weight number in this case, since we have the space. So what it means is that on this F principle is that the amplitude that we multiplied at this sinusoidal component will converge in a faster way, right? So we will get quite well this coefficient for this one that describe what is the high frequency signal. We will have we will be quite slow in converging. And you can actually see on this plot here, we see that overall we converge quite quickly to the overall big structure of our solution, but it takes quite a lot of time to get all these fine structure in place. An interesting part is that traditional, I say also naive kind of solvers like Jacobi or Gasseidel solver, actually they work in the opposite way. They converge on a small scale first. If you use, for instance, if you solve the Poisson equation on 2D, in the case of Jacobi solver, this has very fast, very easy formulation. And you realize here actually that the interaction and the calculation of a certain point only depends from the local neighbor. So this means that the local structure will be resolved quite quickly. However, the propagation to the global structure will take time. So global like solver like Jacobi, Gasseidel will actually converge faster on this, but it will take time to do this part well, because this neighbor interaction need to propagate. So the idea here is really to take the best of the two worlds when integrating this new machine. This is combining low frequency and high frequency solver. this is something that is already known as typically done on multi-grid methods. So we can just devise a very simple idea. It's just very naive, and also just to give some starting point for a discussion on multi-grid solvers or on combining iterative solver, classical iterative solver, and PINN. So since we know that the PINN are quite good on the coarse grid, so on getting the overall structure, we can use the PINN first on a coarse grid, find the solution, and then using some iterative solver plus other multi-grid solver to actually resolve. But the basic technology we are going to use here is actually to use the deep learning solver for solving the coarse part, and then use the Jacobi, and decided to solve the low scale part. So we can do the methods. You see that the results of a hybrid solver, if we go in usable time, in terms of minutes, to quite a low error compared to the error that we have on using directly the PINN. There are some performance results. Basically, the take-home message here that we are in the range of competing with state-of-the-art CG. Still, comparison are quite difficult to make, but we are getting there. So we see a future. Of course, the next step, this is kind of not elegant, to have these two separate steps. Probably, going to forward, the best will be to integrate to the numerical scheme, like Jacobi, directly within the neural network. An interesting starting point is to look at this discrete PINN. They actually encode within the residual function the discretization part. However, this part needs simulation data for the training part. However, it's very elegant way that show what are the possibility of combining numerical techniques within the neural network, and I think is very good and promising approach. So I'm running late for this talk, and I want to just conclude very briefly. I just presented the PINNs and what is the main innovation from my perspective. I also saw that PINN performance is still lagging behind, even though some tuning is lagging behind the state-of-the-art linear solvers or solver used in scientific computing. I also show, and I here concluded my presentation, that is very promising to look at how to integrate a new emerging neural network technique within traditional scientific computing solvers. We are still very much in the infancies, and there's a lot of work to do. So it's quite an exciting part to work on. Thank you very much for your attention.
Thank you, Stefano, for the lovely talk.
Yeah, thank you.
Before we move to Q&A, I just want to mention that if you're interested in future BCAS talks, please do check out our website where we keep our full schedule, and we'll be announcing new talks soon.